So we have an inner product space V and a set X contained in V. X doesn't have to be a subspace. And I prove that the set, I'll call this X perp, this is perpendicular. This is all the vectors in V that are perpendicular to every element in X. That is, the inner product of V and X is equal to 0 for all X in X. And we proved the theorem or the lemma, X perp is a subspace of V. And we also have the following theorem, which is extremely important. So again, V is an inner product space. Let W be a subspace of V. Then, so if the dimension of V is n, and the dimension of W is k, then we know that W perp is a subspace. Its dimension is n minus k. And a proof goes as follows. We know from what we've just been doing that every vector space and every subspace in an inner product space has an orthonormal basis. So let E1 up to EK be an orthonormal basis for W, that EK plus 1 up to EN be n minus k vectors, such that E1 up to EK plus 1 up to EN is an orthonormal basis for the whole vector space, for V. I claim that these n minus k vectors is a basis for W perp. And if that's the case, that certainly implies that the dimension of W perp is n minus k. And how do we prove this? So let V be any vector in the vector space, and let the coordinate vector for B with respect to this basis, which is E1 up to E sub n, be x1 to xn. So what this means is the vector V is x1 E1 up to xn En. That is, E1 up to En is a basis. Every vector has a unique representation as a linear combination of the basis vectors. So V is x1 up to E1 up to En. So the vector V is in W perp if and only if the inner product of V with W is 0 for all W in W. But because E1 up to EK is the basis for W, that is W is the subspace spanned by E1 up to EK, V is in W perp if and only if the inner product of V with E sub I is 0 for all I from 1 up to K. But the inner product of V with EI That's the inner product of this, summation xj ej, inner product with ei. J goes from 1 up to n. This is summation, j goes from 1 up to n, xj, inner product ej ei. But this is delta ij. This is the Kronecker delta because ei, e1 up to en is an orthonormal basis. So the only time this isn't 0 is when I equals j, in which case it's 1. So this is equal to xi, which is 0. So if and only if v is a vector of the form summation, I goes from k plus 1 up to n, xi ei. So if v is in W perp, then v is a linear combination of ek plus 1 up to en. So the dimension of W perp is n minus k. And in fact, every vector v can be written uniquely in the form, let's say W plus W prime, where W is in W and W prime is in W perp. So that really is a very nice result. What I want to talk about for the rest of today are some inequalities that derive from inner product spaces. And there are several. The first is called Bessel's inequality. The second is the Cauchy-Schwarz inequality. And the third is the triangle inequality. And these are all fundamental facts that are used everywhere in mathematics. So we'll start with Bessel's inequality. And so we have an inner product space V, finite dimensional, and B, E1 up to En, is an orthonormal basis. For V. That means this is a basis, so these are linearly independent vectors that span the vector space V. The inner product of any two different ones is 0, so they're mutually orthogonal, and each of them has length 1. So let V be a vector, and we can write V always as some, let me write the coefficients as C sub I, E sub I goes from 1 up to N. So this is the unique expansion of V as a linear combination of the basis vectors. So the coordinate vector for V with respect to the basis B is C1 to Cn. And C sub I, which is the inner product of V with the basis vector E sub I, is called the ith Fourier coefficient. And in analysis, if you study Fourier series, that's a special case of this kind of construction. And the theorem, which is called Bessel's inequality, says that E1 up to En. Well, let me actually start this on a new page so I have enough room. So Bessel's inequality says the following, that V be an inner product space not necessarily finite dimensional. Let E1 up to E sub n be a finite orthonormal set of vectors in V. And let C sub I be the inner product of V with E sub I, be the ith Fourier coefficient. Okay. I mean, the definition of this is the ith Fourier coefficient with respect to this finite sequence of vectors. Then, and this is the inequality, if you take the sum of the squares of the Fourier coefficients, that's equal to or less than always the square of the norm of the vector. So this is an inner product space. So every vector has a length, square root of the inner product of the vector with itself. And we have this inequality. For any finite set of orthonormal vectors, the sum of the squares of the Fourier coefficients is bounded above by the square of the length of the vector, which is the inner product of the vector with itself. And for the proof, we do the following calculation. Suppose we let V prime be equal to the vector V minus the sum, I goes from 1 up to n, C sub I, E sub I. So I have the vector V, let's just remember, note, we're given a vector V, we compute C1 up to Cn, from that we get a vector, which is summation C sub I, E sub I goes from 1 up to n, and we take V minus this, and we call that V prime. And now we take the inner product of V prime with itself. Now the inner product of any vector with itself is greater than or equal to 0. It's 0 if the vector is 0, and it's strictly positive if the vector is non-zero, but it's never negative. So this is greater than or equal to 0. So let's just compute this inner product. V prime is V minus summation Ci EI. I goes from 1 up to n, comma, the same vector V prime. V minus summation I goes from 1 up to n, Ci E sub I. Let me expand this by bilinearity. This is V minus summation Ci EI minus, let me call this J just so I don't have the same letter being used twice, minus summation I goes from 1 up to n, Ci EI, that inner product with V minus summation Cj Ej. J goes from 1 up to n. Let me expand this. So I have 0 less than or equal to, this is v comma v, minus v comma this sum, minus this sum comma v, minus times minus is plus, plus summation CIEI, summation CJEJ, inner product of all that. So let's see, what is all this? So this is the inner product of V with itself, minus summation J goes from 1 up to N, V E sub J times CJ, right? I'm just using the bilinearity here, minus summation I goes from 1 up to N, C sub I, EI comma V, plus now I have a double sum, I goes from 1 up to N, J goes from 1 up to N, CI, CJ, inner product of EI, EJ. Now, VI, EJ, that's just CJ. That's the definition of the Fourier coefficient. So I have V comma V minus summation, J goes from 1 up to N, CJ, and this is another CJ, so that's CJ squared. And the same thing happens here. This is summation, I goes from 1 up to N, C sub I, and the inner product of EI with V is the same as the inner product of V with EI. That's just, again, the Fourier coefficient, C sub I. So we get another C sub I, so that's C sub I squared. Here, the inner product of EI and EJ, that's just delta IJ. It's 1 if I equals J and 0 otherwise. So the only time we get a term here is when J is equal to I. So we get plus summation, I goes from 1 to N, C sub I squared. And these three terms, they're the same terms of minus, minus, and plus. That means these cancel. Bring this over to the other side. Whether I use the letter I or J doesn't matter. I get summation I goes from 1 up to N, C sub I squared, is less than or equal to the inner product of V with itself, which is the length of V squared. And that is the proof of Bessel's inequality. In some of the exercises, we'll see some applications of this, but this is Bessel's inequality. All right. Next, I want to prove the Cauchy-Schwarz inequality. And there are many ways to do that. In calculus, you might learn that the Cauchy-Schwarz inequality says summation xi yi squared is less than or equal to summation xi squared times summation yi squared. And it's not obvious from this where the linear algebra is, but we'll derive this in a moment from the general statement, which is much stronger than this. And in order to prove Cauchy-Schwarz, so to prove the Cauchy-Schwarz inequality, we have to recall the quadratic formula for solving a quadratic equation. So this is hopefully what you learned in high school, if not in pre-calculus. If you have the quadratic f of t equals at squared plus bt plus c, And quadratic means the t squared term actually appears, so a is different from 0. The solutions, t, are equal to minus b plus or minus the square root of b squared minus 4ac over 2a. That, I hope you know, is the quadratic formula. And how many solutions are there to the quadratic? Well, there are 3 cases depending on what's under the square root sign. So if b squared minus 4ac is positive, then this is plus or minus something. We have 2 solutions. If b squared minus 4ac is 0, then this is 0. The only solution is one solution, t equal to minus b over 2a, because that's 0. And if b squared minus 4ac is negative, then we have 0 solutions in the real numbers. We're not looking at complex solutions here. So this is the fact that we have to remember. And the other comment is, if f of t equal at squared plus bt plus c has no solution, that means the graph never crosses the x-axis. It's either always above the x-axis or always below the x-axis. So either f of t is greater than 0 for all t, or f of t is less than 0 for all t. Now, no solution, that's the case when b squared minus 4ac is negative. That's the case when b squared is less than 4ac. Now, you can always, a is non-zero. You can always multiply by minus 1 if you have to, and assume a is positive. So if a is positive and 4ac is bigger than b squared, 4ac has to be positive, a is positive, means c is positive. C, if you plug in t equals 0, c is equal to f of 0, so that would be positive. So if b squared minus 4ac is negative and the leading coefficient a is positive, that means c has to be positive. F of c, the function takes on a positive value, and that means your parabola is always above the x-axis. It's always either always above or always below. If c is positive, it's above, and that's the case. So this is the Cauchy-Schwarz inequality. It has a beautifully simple formula. We have V in inner product space. So for all vectors, u and v in the vector space, the inner product of u and v, that's some real number. Could be positive or negative. Let's take the absolute value. So it's always greater than or equal to 0. Is less than or equal to the length of the vector u times the length of the vector v. That's the Cauchy-Schwarz inequality. And let's just see an example of this. This is the most important example. In Rn, if we let u be the vector x1 to xn, and v the vector y1 to yn, the inner product of u and v is summation xi yi. It's the sum of the products of the corresponding coordinates. The length of u is square root summation xi squared. The length of v is square root of summation yi squared. So these are the simple formulas for the inner product of two vectors in Rn with the standard inner product and the length of a vector. And what this inequality says is that the absolute value of this summation, so x1, y1 plus x2, y2 up to x sub n, y sub n, that in absolute value is less than the sum of the squares, square root, times the square root of the sum of these squares. Or what you often do is square it to get a prettier formula. You get that for any real numbers, x1, y1 plus x2, y2 up to xn, yn, that squared is less than the sum of the squares of the x's times the sum of the squares of the y's. So this is the basic, most useful inequality in analysis, and it's a special case of the Cauchy-Schwarz inequality in a vector space. So there are many ways to prove it. One clever way is to reduce everything to the quadratic formula. So let t be any vector in R, any scalar, any number, any real number, and consider the vector tu plus v. Take the length of it and square it. So of course, the length of any vector is greater than or equal to 0, and the square of any number is greater than or equal to 0. This is greater than or equal to 0. But the square of the length of the vector, any vector, is the inner product of the vector with itself. So it's the inner product of tu plus v with 2u plus v. Let's expand that. That's tu plus v times inner product v inner product with tu plus v. This is equal to tu inner product with tu. That's t squared inner product of u with itself, plus t times the inner product of u and v, plus v, take this t out, t times the inner product of v and u, plus the inner product of v with itself. So what is that? So this is the length of u squared times t squared. uv equals vu because an inner product is symmetric. So this is plus 2 times the inner product of u and v times t, plus this constant, which is the length of v squared. So this is greater than or equal to 0. Now, what do we know about a quadratic polynomial? If it's always greater than or equal to 0, the only two possibilities are it's always positive or it touches the x-axis in just one place. If it touched the x-axis in two places, it would be negative sometime. So in this case, the discriminant that b squared minus 4ac is positive. In this case, b squared minus 4ac sorry, in this case, b squared minus 4ac is negative. It has no real root. And in this case, b squared minus 4ac is greater than or equal to 0, but it's not greater than 0 because then there would be two roots. It's equal to 0. So what we can say is b squared minus 4ac, remember you have the standard form of a quadratic, at squared plus bt plus c. So b squared minus 4ac is less than or equal to 0. And in this case, what are the a, b, and c? The coefficient of t squared, this is my a. The coefficient of t is this, that's my b. And the constant term is c, that's this. So to say that b squared minus 4ac is less than or equal to 0, or equivalently, b squared is less than or equal to 4ac, this, this is 2 inner product of u and v squared is less than or equal to 4 times a times c, which is 2 length of u times the length of v, all squared. So when you take the square roots, you get the absolute value of 2uv is less than or equal to 2 times the length of u times the length of v. The 2's cancel. And I have my Cauchy-Schwarz inequality. That's the proof. And this is really a beautiful thing to remember. So that for any vectors u and v, the inner product of u and v is always, at most, it's bounded above by the length of the product of the lengths of the vectors. This is what we just proved. And I will give it a star because it is so central to a lot of mathematical work. And one consequence of this is the Pythagorean theorem. So Pythagorean theorem. What does the Pythagorean theorem say when you learned it in elementary school? You have a right triangle. The sides next to the right angle are a and b, and the hypotenuse is c. And it says that a squared plus b squared is c squared. If we call this vector v and this vector b, if we call this vector u and this vector v, this vector is u plus v. And what was the formula I had when I started to prove the Pythagorean theorem? I took vectors u and v, look at the combination tu plus v. The length of that squared is certainly greater than or equal to 0. And when you expand it, you get the length of u squared times t squared. plus 2 inner product of u and v times t plus the length of v squared. So again, we can picture this like this. We have a vector u, a vector v, they're perpendicular. We can think of this as u plus v. And if u and v are perpendicular, which means the inner product is 0, then we get 0 less than or equal to u squared t squared plus v squared. For any t. Sorry, let me write this down more carefully. So tu plus v squared, if uv is 0, this is equal to the length of u squared times t squared plus the length of v squared for all real numbers t, no matter what number we pick. So if we pick an interesting number, for example, t equal 1. Let's just make it easy. Let t equal 1. This says the length of u plus v squared is the length of u squared plus the length of v squared. That's all there is to it. So actually, I could have made it much simpler, simply that if I take the length of u plus v and I square it, this is the inner product of u plus v with itself. That's uu plus uv plus vu plus vv. These are 0 if the vectors are perpendicular. So this is just the length of u squared plus the length of v squared. So actually, just this one simple line is a proof of the Pythagorean theorem. All right, well, I wanted to prove those two inequalities, and I did. So I think I will stop right now.